In this video, I wanted to give you an overview of the two labs, the parameter identification lab and the modeling lab for our SMAC course. All right, so let's get started. In the first lab that I wanted to talk about, we were looking at a mathematical model. So if you look at the lab write-up, there's a DC motor and an equivalent circuit, and they walk you through the steps for deriving the equations for a mathematical model that takes a look at this situation that we're looking at with this virtual lab. Okay, so we have the mathematical model, but there are some experimentally determined parameters that you work through and do the calculations for within the lab. Okay, so one of the things that I want you to do with your write-up is to actually derive the transfer function between omega s. Okay, so omega is the rotational angle of the DC motor, and Vm is the input. Okay, so you're looking for this transfer function between omega and Vm, and I just give you this. This is the thing that you need to derive, and I'd like you to show all the steps for how you came up with this derivation. Okay, so once you do the experiment, you'll have the mathematical model, and from there you'll look at doing the parameter identification so that you can plug in and get a specific numerical value for the part that's highlighted here in yellow. Okay, so that's the parameter identification lab. In the modeling lab, we take a similar approach, or not similar, it's a different approach, to where you are looking at doing the model without looking into the box. Okay, so it's a black box model where you're just looking at an input and output, and you don't look inside the system to do any mathematical modeling. Okay, so what we're going to assume here is that we have a first order system. All right, and so you can manipulate the first order system to be this form. Okay, so this form has a gain constant K and a time constant tau. All right, and the reason we write it in this form is it becomes easier to estimate the parameters K and tau, because when you look at your time response, right, if you have a step response, you get something that looks like this, and you can estimate the K value by how high this goes, and you can estimate the tau value by looking at the time constant where it gets to within a certain percentage that they go over one time constant of the final value. All right, so from there you can make an estimate of tau. Okay, so you're taking two different approaches. Some people would call this the white box approach, where you look inside the system and you come up, it's lit up with light. You're trying to figure out exactly what's going on in terms of all the system parameters. And then you have methodology that lets you estimate the system parameters to get your model. Okay, this is the ideal approach, because if you changed one of the models in one of the parameters in the model, you wouldn't have to redo any experiments. Okay, but this black box approach, it's good for giving you an idea of what the system is like, and it's also good for verification, because ultimately when you take a look at these two systems, these should be comparable, where they're not going to be exactly the same numerical values that show up in the transfer function, but they should be reasonably close. Okay, so hopefully that helps you get a picture of what's going on with the first two labs.